Hello and welcome again to my channel. This is video number 2 in the series. In the last video, I had provided an overview of my project and what I have been trying to achieve. Starting with this video, I'm going to do a deep dive into the code. In this video, I will focus on the first step, which is to merge the raw data from the input files and create pairs of data in preparation of feeding the data into Apache Spark. As I said, all my data is on my GitHub. The source data is also on GitHub, and the link to that is on my GitHub repository. I'm going to hop quickly to my AWS Cloud9 environment. I am running the code for the pre-processing on a Cloud9 environment. You could run this on your own local machine, but you'll need to install the AWS CLI as well as set up API keys. You start by downloading my code as well as the source data set from GitHub. So it would be a standard Git clone. I have already done that. From the source data, the two files I am most interested in are dso.csv that has the data on the deep space objects, and hyg data version 3.csv that has the data on the stars. So I'm going to do a quick count on these two files. So that is about 119,000 stars and 227,000 deep space objects. So in my first step, I'm going to combine these two files into a single file. And this is the code which does that, extract, subset, and combine. I will not be using all the data for my data. Here you can see I have applied filters to the source data based on magnitude. Magnitude is an attribute in both the files, and this is a log scale. The bigger the number, the dimmer the object is. Here I have chosen all stars which are brighter than magnitude 8 and all deep space objects which are brighter than magnitude 15. Remember, the bigger the magnitude, the dimmer the star is. So if you want something brighter than magnitude 15, you have to look for magnitude less than 15. And this is standard Python. I load the source data into a pandas data frame and then do a combine. I did add a unique ID called row ID, which is the index from the source file, prepended either with DSO or star. So I'm going to run this and I'll pause it while it is running. So that has finished running, and what it has done was created a new file called combined.v2.csv. What we have at this point is a file which is a combination of the two source files that we have with just the data that we're interested in. We have not yet created the pairs between the data, which we are going to do in a minute. Before that, let's take a quick look at the combined data set that we just created. So we're going to do a quick count over here. And this is 58,742 records. Again, this is all stars brighter than magnitude 8 and all DSOs brighter than magnitude 15. Our next step would be to create pairs between this data. And what we're going to do is find each DSO and each star and create a pair with all the DSOs and stars which are close to it. You might be wondering, why do we need to create these pairs? And that is because of the way PySpark works. When you create a PySpark data frame or PySpark RDD, what will happen is you're going to give it a set of rows. And when it runs, it's going to split these rows across multiple nodes. You have to make sure that each node has enough information to do the compute that you're asking PySpark to do. In this case, we will be asking PySpark to calculate angular distance between each pair of objects. So we have to make sure that in each row of our input, there is enough data for PySpark to do that compute. So essentially, PySpark will need to have the array, the right ascension and the declination of each object between which it needs to calculate angular distance. This will be done by my second piece of code called createpairs.py. Also, I'm not going to pair up all the objects in the dataset. I'm going to loop through all the DSOs and stars and create pairs between other DSOs and stars in a roughly 7 degrees around it. So if I'm creating a pair for everything with M13, I'm going to find M13 and then I'm going to create a pair between M13 and every other star and DSO which is roughly 7 degrees of angular distance in the sky away from it. 7 degrees is a reasonable assumption because 7 degrees is roughly the widest field of view in a binoculars and also the widest field of view which will be available in a finder scope. Beyond 7 degrees, building relationships probably does not have a lot of value. The quick and dirty way of doing that is simply to add upper and lower bounds to array when we are building the pairs. And that's what I've done over here. What I do in this code is to start with, I load my combine v2.csv into a pandas data frame. And then I loop through it and I'm doing some batching of 1,000 records just for performance. Then I loop through it again, and in the inner loop, I add upper and lower bounds to array and declination. And what I say is that only return in my inner loop all records where the array and declination is within 7 degrees of the outer loop's array or declination. So that should give me all objects which are roughly between 7 to 9 degrees away from your source. You'll notice here that for array I put 0.5. That's the reason for that is because array is expressed in hours, not in degrees. 1 hour equal to 15 degrees. So 0.5 hours is 7.5 degrees. So this is a quick and dirty way of doing this. So I'm going to run this code and I am going to pause the video as it runs. So that has finished running and it has created 59 files which have been uploaded into an S3 bucket and folder which I specified in the code. So what have we done so far? So far we have started with 2 raw data files. We have filtered out the data that we don't want and we have created pairs between the data that we have in preparation of feeding the data into Apache Spark. In my next video, I'm going to spin up Apache Spark clusters in EMR and I'm going to use them to process these raw files that we created, and that will build out the relationships for our database.